for coming. It's exciting for us to be here and talking about a project which has been a long time in the making, but more recently has got to a good state of maturity, and so we're pretty proud to be able to get up in front of people and talk about it. I have a talk today that's a talk that I've been doing for a year or so, and has kind of gradually evolved over that time to get hopefully better and better. In this talk, I make I occasionally make some comparisons to Java or to other languages, and I want to, make it very clear that when I do that, look, guys, we're big fans of Java. We call ourselves Java developers. We, as in my whole team. We love Java, we love its ecosystem, we love its community. When I make comparisons against Java, it's from the point of view of wanting to justify why we've done something differently, to kind of achieve an understanding of what it is that Ceylon's doing and why it's doing it. So let me start. I hope you'll forgive me if I, kind of spend just as few minutes as possible on some, kind of general slides for people who aren't familiar with the project. So what's Ceylon? It's a programming language. It runs on virtual machines. Specifically today, it runs on the Java virtual machine and on JavaScript virtual machines. That's an open-ended list. We have been very careful to abstract the language away from the details, from the finer details of any particular virtual machine, and even from, for example, from the SDK of Java. So Ceylon is a language which is meant to be a little bit future-proof, which can be naturally ported to other virtual machines in the future. Examples of the kind of things we would consider would be, for example, the Dart virtual machine, perhaps .NET, now that some of that technology is being made more available in open source. And, potentially some of our users are very, putting pressure on us to consider an implementation on top of LLVM, which would be make it a natively, more of a native language. What it's not is it's not a language for system programming. This is a language for, more slightly more high-level application development. It's a language defined by a specification. A specification is rather rigorous. And I think, to me, that's something that's very important. I think there's nothing in developing software that makes you really be sure that what you're doing is right than having to actually write it down and write down what you think the system does and what it should do and think through the corner cases. I think specifications are very useful, and they're especially very useful when your users come along and want to know how something's supposed to work. The language has a syntax which, when you first see it, might look, rather boring. It's a very conventional syntax, inspired, that very much falls into the tradition of the languages that descend from C. But, once you scratch the surface, you'll find that the syntax is actually extremely flexible. Ceylon has a type system that is very powerful, simple but powerful, and people, the kind of words people use to describe it are elegant, and people get very excited about the type system, which is quite different to, which is quite distinct. The language has built-in modularity. Modularity is central to everything we do as software developers. It is the end goal of the whole discipline of software engineering. It is curious that languages have traditionally featured very poor support for modularity, and it's very encouraging that today, we see languages starting to take that seriously. We hope in future that for example, what Java 8 Jigsaw project provides will be something that we can reuse, and that our module system can be implemented on top of Jigsaw. Ceylon has its own language module and SDK. This is important. This is an important aspect of being able to run across multiple VMs. It's also a very important aspect of being able to make the whole development experience better. When you look at the APIs that are, form part of, the Java SE or of, JavaScript that you get with the language, what you get with the language, which is not much, but especially, I'm particularly thinking of Java SE, you're seeing things that were designed 15, 20 years ago, a lot of craft that never ever gets fixed. And a lot of it's plain wrong. A lot of it's very difficult to use. So we wanted to modernize and improve, the basic APIs that you work with all the time. Ceylon is a language of static typing. What that means, the only reason you have static typing in a language is to have tooling. It is a primary goal of the primary focus of the project to have excellent tooling in terms of IDEs and command line tools, etc., etc., etc. Where can you use Ceylon? You can use Ceylon in Java SE together with the Ceylon module runtime, which is based upon JBoss modules, the core of Wildfly application server. In future, we hope that we can swap that out and replace it with Jigsaw. You can run Ceylon in any OSGI container, Eclipse, Apache, Felix, in application servers that are based on OSGI, Wildfly, Glassfish, etc. A Ceylon module is a valid, comes straight out of the compiler as a valid OSGI module. It runs on Vertex, which is a project sponsored by Red Hat to bring the Node.js programming model to the JVM. So Vertex features first-class support for Ceylon. You can use Ceylon in Node.js, compiling to JavaScript. You can use it in a web browser together with some, Node.js has its own module system, and Ceylon is compatible with that. In a web browser, you'll need a common JS or require JS or something like that, and then you can run your Ceylon modules. You can load your Ceylon modules via the require function. In Ceylon 1.2, which is basically ready at this point, you can run a Ceylon. You can repackage a Ceylon module as a war using the command Ceylon war, and you'll have a Java EE application. Finally, as Steph demonstrated yesterday, you can run Ceylon on OpenShift, which is Red Hat's cloud. Everyone wants to know about interop immediately. Interop is extremely important. We've spent years on making Java and JavaScript interop work very well. In Ceylon, you have a choice when you start writing a module. You can write a module that is completely cross-platform, that will run on any virtual machine that Ceylon executes on. And that's a well-defined thing. You can't accidentally start using stuff from the Java SDK or stuff that's JS-specific. On the other hand, you can make a choice to target one or the other of the platforms that Ceylon runs on, in which case you can explicitly, for example, import part of the Java SDK and start using APIs from there. And that's a well-defined thing, and you always know that that's what you're doing. Interop with JavaScript interop for a static language to call a dynamic language is actually often a challenge. So interop with JavaScript is either via a language construct we have, which kind of turns off the type checker within a certain block of code and says, okay, let me just write some code and call some stuff and just let me do it, right? Or via a thing we call a dynamic interface, which ascribes types to a native JavaScript API and lets you use that API in a type-safe way, assuming that you've written that dynamic interface correctly. in future, we hope to be able to reuse some of the definitions in that the TypeScript project has worked on for that interop. Some, very unique things about Ceylon. First of all, the fact that it's designed from the ground up for multi-platform use. The fact that it has reified generics along with a type-safe meta model for introspecting, information about the schema of your program. This allows some very powerful and useful stuff, which I'm not going to get into here. Union intersection types are the thing which, people get most excited about in Ceylon, and which you see now other languages, and now heading down this path. It's the foundation of some of the coolest things in Ceylon, like, unambiguous type inference, and flow-sensitive typing, which are, make the language a joy to use, make the type system, make it just much nicer and more enjoyable to work with static typing. The representation of function and tuple types in Ceylon is especially elegant. There's no explosion of function types, function 1, function 2, or Java's single method interface types. There's a single interface callable and a single class tuple, which are capable of abstracting over functions and tuples of arbitrary arity. This means that we can write higher order abstractions, functions which abstract over functions and tuples, over function and tuple arity, which means some pretty cool stuff, things like promises, libraries, and stuff like that. Overall, what I'm talking about is a language with a simple, unified type system, and then elegant syntax sugar, which takes care of the verbosity that can arise out of a very simple type system, okay, without humming readability. So, what I'm going to do is start to explore the language through, a series of very simple examples. The purpose of choosing simple examples is that they fit on slides. That's not to say that this is a language which is focused upon solving trivial problems. It's to say that I want the problems to be things that you guys can comprehend just by looking at one slide and understand what it is that I'm trying to do. All of these problems are kind of trivial examples of things that actually scale up and that actually occur in more complex contexts. So first of all, I always start with an example of a function which has multiple outcomes, multiple kinds of ways in which it can terminate, multiple kinds of things it can return. So imagine that I have a function that might return a file or a URL, or might not return anything when I give it a path. Now, file and URL don't have any really interesting common supertypes. They both come from external libraries that I don't have control over. I can't introduce a file or URL interface and add it to them, let's say. And so if I were working in Java, the return type of my function would be object, I suppose, or something uninteresting like that. The problem with that is that I lose a lot of precision when I do that. I lose the information from the type signature that this function can either return a file or a URL. So from the point of view of the caller of this function, he gets back an object, and then he has to check whether it's a file, check whether it's a URL. The first problem you see here is that after I've just asserted that result is a URL, I then have to reassert it right here, which is just crazy, and it's amazing that almost every language on earth makes me do that. There is nothing else that result could possibly be here, so the assertion is completely superfluous. And then I guess I have to another interesting thing here is that how do we handle the case where the string doesn't represent any valid path of anything? I could return null, I guess. And sometimes in some APIs, that's what I do. but there's a tendency to avoid null as a return value in Java because the fact that a function can return null is not something that's captured within its signature, so it's very easy for the caller to forget to miss that case. So often people will choose to use an exception instead, which carries a little bit more information than null. And so, we have a catch block here. And the trouble is, if at some stage I change parse path so it could return something else other than a file or a URL, this code's not going to break, and the compiler can't find this code for me and flag to me that this is something I need to change. So, that's quite unacceptable. In Ceylon, I have this notion of a union type, and this is the most trivial use of a union type. So, instead of returning object or throwing an exception, what I would typically do is consider each of those possible outcomes as the cases of a union type here. So I have a function that returns a file or a path or a syntax error. And now, from the point of view of the caller, well, he just handles the various outcomes using switch. The difference being that the compiler can now validate that I've exhausted all cases of the return type of, or all cases of result, and no other cases, right? So there's a lot more that the compiler can do here. Secondly, we can see another nice thing here of flow-sensitive typing. Here, when I assert that something's a URL, I don't then have to immediately follow it by a typecast. So in Ceylon, the type of a value is adjusted by the compiler within scopes according to the things we've asserted about the type within the flow of code. There's some, obviously this is a lot more powerful. We can have a case which handles multiple outcomes, and so we have file or URL there, or the case of syntax error and an else. We can do the same kinds of things with if that we can do with switch. It's all completely integrated into the language. Okay, so that was kind of a contrived example. Now let's look at an example which is absolutely not contrived, which is something that comes up almost every day. Okay, and that's the case of a function which might return null. Okay, this is just a special case of the thing we were talking about there. So the interface map has an operation called get, which accepts a key and might return an item, or it might return null. Okay, so here we have some syntax sugar. We have this item question mark. I usually say maybe item. I usually pronounce that as maybe item. And that just literally means null or item. Let's see what the hell it is I'm really talking about here. So let's, sorry? Oh, forgot. Where am I? Colors and fonts, right? Text font. That can be too big, right? Oh, sure. Okay. Is that better? So let's I've done this example a million times. Well, let's do the make. Here we have something that's a maybe string, and let's try to print. Let's try to print it, right? And I get an error. So the error says, the right operand must be of compatible type. Maybe string is not a string. All right, well, okay. So let's see why it's complaining about that. This code was compiled in Java. What the hell's wrong with it? Well, let me first tell you what plus means, literally. Okay, plus means the method plus of this interface called summable. So now we can see that, okay, the argument isn't assignable to the parameter other of plus. Maybe string is not assignable to string. Well, let's see what that what that really means. Okay, well, now that makes sense, right? I have something that's either null or string, and I'm trying to assign it. Well, let's just check what null is, right? So null's a class, all right, of a single. It's a class with a single value, right? This object null, okay, and it extends something called anything. What's anything? Okay, anything is the abstract supertype of all type. Okay, so this is the root of the type hierarchy, all right? And it's an enumerated type. It has two disjoint subtypes, null and object. So hold on a second, all right? So it has two subtypes. One is null, which we've already seen. It just has a single instance, null. And object is, it's everything, right? The whole universe descends from there. Okay. So, obviously, this thing over here, a null, isn't an instance of string, right? These are disjoint. Okay, so now it's obvious that this isn't well typed. Okay, so how could I handle this? Well, I could use an assertion. Okay, I could say assert exists. You're like, oh well, what's this? Is a totally ad hoc, hacked-in thing exists in the language. Now my code compiles. I'll come back to that in a second. Now my code compiles, right? And down here, arg has type string. Well, that's that flow-sensitive typing I just talked about, right? Now I've done an assertion, and the type of this arg has changed. All right. Now I'm going to tell you what that literally means. Okay. Exists is not something special. It's just a syntax sugar. It just means is object. All right. That's that object class we just saw. All right. So now I said arg is object, all right? So what? So wait. But down here, arg is string. How does that work? Well, that works like this. Ceylon compiler doesn't throw away any information, okay? We already knew that arg was a string question mark. That's the type of this expression here, right? Compiler already knows that what it has is a maybe string, right? So it already knew that. So it already knows it has something that is a null or string and object. This is the syntax for an intersection type, guys. Okay, we've seen union types, now we're seeing intersection types. Intersection distributes over union, which means that I have that type there. Who knows what the type object and string is? Simplified. String, of course. String is a subtype of object, and therefore, who knows what the type object and null is? Null and object, recall, are disjoint types. Yes, the empty set, which we call nothing, okay? The bottom type, the type which is assignable to all other types, okay? The empty set. So in Ceylon, that's called nothing. Who knows what the union between string and nothing is? Of course, trivial. So thus, we arrive at string, okay? It's the kind of reasoning that the compiler does very quickly and very easily. Even better, this is the kind of reasoning that programmers are very well equipped to do by ourselves, right? Reasoning about sets is easy, guys. Reasoning about sets is one of the most intuitive things. Nobody in high school when they first encounter the notion of sets is ever sitting there moaning, oh man, this set theory is so hard, right? That doesn't happen, right? Calculus, maybe. Set theory? No, it's easy. Okay. The point of all this is that by bringing null into the type system as an ordinary class, we wind up with a system which is far more capable of reasoning about nullness and helping us find potential null pointer exceptions in our program. In Ceylon, there is no way a null pointer exception can ever possibly occur. Or even another exception which is essentially the same thing. Okay? You have to explicitly over here have something which explicitly obviously can fail, i.e. an assertion. Before you can have a failure of that nature. And obviously we can use an if instead and escape that whole possibility. Okay? So this program can't possibly fail with a null pointer exception. Okay? I have to explicitly, I would have to explicitly throw an exception or explicitly assert something false for an exception to occur. So there's lots of nice syntax sugar for working with null in Ceylon, but at core it's just an ordinary class, and the reasoning that applies to null is just the reasoning that applies to any other kind of class, including classes that you guys would write. Okay, a second useful thing that we get from union types is the ability to represent heterogeneous collections. So let's consider that I'm in Java, and I create a list using arrays as list, and I give it some integers and I give it some floats. What kind of list do I get back? Well, that's ambiguous in Java. All right, integer and float potentially have lots of different super types, and so I have to explicit on that side what kind of list, and then the compiler will check that really is that kind. Even then, I lose some information. When I come out and grab an element back out of my list, I get a number, and I don't really know, which are exactly other cases that I need to handle. In Ceylon, if I do something similar, so let's let's create an array list of integers and floats. Sure, that was my silly example, contrived example. So I got a list here. Oops, I don't want to show you the answer. Now, what kind of list do I have here? By now, somebody in the audience should know the answer. What's the type of what's the element? What's the inferred element type of list? Huh? Integer or float. Correct. Okay. So if we fill in that inferred type over here, where's my quick fix? This is not very quick when I have to sort through a list of hundreds of them. So there. Ah, yes, it was. Okay. That is the type that's inferred. This is the most precise possible type, guys, right? Anything which I could write over here, anything which I could soundly write over here, let's say object or whatever, is a supertype of this type. So this is a property of our type system called principal typing. Okay, even when I'm using type inference, every expression has a unique, most precise principal type, and that makes type inference much more powerful. I can use type inference in lots of cases, so I can get away with just writing this. Then when I get something out of the list, give me the third element, I get the right type back. Obviously, I don't have to write that type in explicitly either. It's inferred. Right. Now, this may look a little contrived, right? You're like, wow, how often do I create a list of integers and floats? Okay, and I understand that feeling. What you'll have to believe me is that this actually occurs in practice much more than you imagine. Right? And in fact, that we use this kind of stuff, this kind of reasoning, very much in Ceylon, especially when writing generic code. That's what we've just seen. Okay, so in order to make a little bit of an attempt to convince you that that's really true, let's consider some less contrived examples. Okay, so iterable, which is an interface we have that represents streams. Okay, streams are very common in Ceylon. So we have a little syntax sugar. You know, these curly braces with a plus or a star in them. That means the type iterable. It's just a syntax sugar. So that's not scary. Okay. We have an operation on iterable, a method on iterable called follow, which essentially says add an element at the start of the stream. All right, that element can have any type, right? That's the type other in that type signature. And so what is the return type? So what is the type of the stream I get back? Let's just consider what kind of, do I have a stream here? Yeah, I have a stream. List is a stream. So if I say list.follow, and I put a string at the head of it, then I get back the right type. Now I have a stream of integers, floats, and strings. That just comes out of the definition here of follow, that it returns the union of element and other. That's a rather elegant definition of that function, I believe. Again, you know, all these types can just be inferred. I never have to write in any of these types explicitly. An example with an intersection. One of my favorite operations ever is coalesce. So let's go back over here and let's say and let's make this a stream with null in it. So now I have a stream which has null, right? You guys can see there. And now if I coalesce it, I get back a stream without nulls in it. Let's look at the definition of this function. It's defined as returning the element type intersected with object. How does that work? Remember, object was any type which is not null. It is joint. So that eliminates, so that intersection with object, you know, the compiler does this reasoning automatically, obviously, right? You know, it infers that. That intersection with object eliminates here the case of null. I think that's pretty elegant. So, you know, that sounds kind of good. You know, the handling of null and stuff in the language seems to be working out. I can write these nice functions like coalesce and it works out nicely. But then we ran into a case which really bothered us. There's an interesting function called max, which comes up from time to time. I want to take the maximum value of a stream of values. And the question is, what should be the return type of the max function? Suppose I have a stream that I know at compile time is non-empty. Then I know max will return a value, right? The maximum value of the stream. Suppose I have a stream that I know at compile time is empty. Then I know max returns what? Null. No, there's no value for it to be the maximum, right? What about if I have a stream that statically at compile time I don't know whether it's empty or not? Then it should return, if it's a stream of integers, maybe integer, right? Could return null if it stream's empty, or a value if it's not empty. So how would we write down the signature of this function? Well, a first attempt would be to handle the case I don't know whether the stream's empty or not. Okay, the star means a stream which I don't know whether it's empty or not. Okay, and you know, so max returns maybe value. But look, guys, most of the time, you know, what if I just every time I write max of x comma y, I have to handle the case of null? That would be awful. Can you imagine how much it would get in the way? It would be terrible. It'd be the worst language ever if nulls keep popping up in these kind of types, nulls which are type nulls keep cropping up in contexts like this, where I damn well know that the function can't return null. So what do I do? Do I have an extra max non-empty function? You're telling me my language I have to have duplicated functions for every function, max, min, and every function of that nature? First. Terrible. So for a lot of thinking, what we arrived at was something kind of strange. So the solution was to add a second type parameter to iterable. You can see that this type parameter has a very interesting constraint on it. That absent satisfies null. That's an upper bound on that type parameter. This syntax says that absent must be a type. The type argument to the type parameter absent must be a type which is a subtype of null. What are the possible type arguments then? You guys tell me. What are the subtypes? What are the subtypes of absent, of null? Null and nothing, precisely. Very good. So what do they correspond to? We can look at it by looking at the type of the first operation. If absent were nothing, then we would have nothing or element. So the type of first would be just element, right? That corresponds to, thinking back, the case where I have a stream that I know is non-empty, right? Is that clear? People agree with that? What if absent were null? If absent is null, then the return type of first is maybe element. That corresponds to the case where I don't know statically that the stream is non-empty. Okay? So when I go back here, so that explains this syntax, which might have looked a little bit scary when you guys first saw it, right? This syntax for streams. If I expand this type abbreviation and desugar it, you see that plus corresponded to the case of nothing here, right? Make sense? Or if I had a star here, that corresponded to the case of null there. Good? So far? What's interesting about this then is that I can write a function like max, that propagate. Okay, this looks a little bit scary the first time you see it. The actual, this is the type of the parameter. That's the type of the parameter. That's the return type. These are the type constraints. This function propagates the type absent of the iterable into the return type of max. Thus, if we have a, what was this one? This was a non-empty stream originally, right? So let's say max of follow. Propose me that. Mick. What's going on here? Ah, sure. Okay. So max of some integers, right? I can't compare floats and nulls to integers. Obviously, that was what the error was telling me. So here, Give me a non-empty stream. Okay, good, better. So here I have what is a stream of, a non-empty stream of integers. And so the return type is, of max, is integer, right? If I take away that extra information, then I know that the return type of max must be maybe integer. Okay. So that was a solution to the problem of how to write down the return type of max, so that we always get the right. So we always get the right return type depending upon the emptiness or non-emptiness of the argument we pass in. And it's important this, okay? This shows you that in the design of your language types, like iterable, if you're going to have type-safe nulls, right, you have to, that's kind of works out to be not very useful unless you also think about this concept of type-safe emptiness or non-emptiness, okay? Having type-safe nulls without type-safe emptiness or non-emptiness actually winds up to be, would turn out to be rather nasty. Okay, I have 10 minutes left. So let's switch from thinking about unions and intersections to exploring a kind of a different kind of multiple return values. This is a function which can return, two values at the same time. All right, so I have a function which returns, which parses a string and returns a protocol and a path. Okay, two values, right? In Java, I would be required to create a new class called protocol and path to represent the return type. What's wrong with that? Nothing. It's all right. It's okay. It's not broken. So occasionally, it's convenient to not have to create a class just to have a function that returns more than one value. And so Ceylon has something called tuples. Okay, we write a tuple between square brackets. Okay, so to instantiate one, we've seen how we write streams between braces. Okay, we write tuples between brackets. So to instantiate one, we write its elements between the brackets, and to represent and to write down a tuple type, we write the types of its elements between brackets. Now we can extract its elements of type. So wait, let's go and explore tuple a little bit further, right? So let's get rid of all this rubbish and write down a tuple. Okay, good. And let's say, let's get its first element is X, let's say, type integer. Y, again, type integer. Third element, type string. Fourth element, type null. Cool. So lots of languages have tuples, right? It's not really any great achievement to have, integrated into the type checker reasoning about tuples. But that's not what I did. Okay? There are no tuple types in Ceylon apart from a trivial little syntax sugar. This means this. Okay? Obviously, we never write this, but that's what it means. And that's how what the type checker uses to reason about tuple types. Because tuple is just a class written in Ceylon. Okay. Steph's wonderful backend does some crazy stuff with tuples, okay, to make them efficient on the JVM. But you guys, as Ceylon developers, don't see that. Tuple is just, and the type checker certainly doesn't see that. So tuple, what is it? It's a, according to itself, it's a typed linked list. Each instance of the class tuple is a link in the linked list that carries a value and the type of the value, right? So you can see over here, this is, you know, what all this means is tuple of, comma empty. Right? So you can see that I'm instantiating a const list here, right? And here is a linked list at the type level, right? That's a linked list of types. Agreed? So notice there's nothing, you know, this is just, you could write your own class tuple which does that, which does exactly this, right? Let's hide this type, I guess. And notice all this is all still well typed. Why? Well, hold on. I should explain what, I should tell you what this means. That means that. So over here is an operation first. This means make. So you can achieve exactly the same functionality with a class you write yourself. Right? Nothing special about this from the point of view of Ceylon's type system. We're completely able to represent tuples within the type system itself. 5 minutes left. The cool thing about having tuples is that they're deeply related, is that they came into the language because it's the way we use to represent function types. So let's consider a function that accepts, what was the type of this tuple? Integer, string, right? So let me write a function f that accepts integer and returns who cares, x plus y, why not? Now, if I take a reference to this function, that's how we write a function type in Ceylon. We're saying it's a function that accepts an integer, string, and returns an integer. Now, by now, you guys should know what I'm going to do next. That's just a type abbreviation. What does this mean? That, right? That's a callable with the return type integer and the parameter type that we just saw above, right? That tuple type captures the parameter types of the function. Given that there's such a natural relationship between function types and tuple types, what does that mean I can do? It means I can do shit like this. I can spread a tuple across the parameters of the function. Right? This is a spread. I don't know if you guys seen this syntax before. It's like the spread operator in Groovy, right? Difference being that that this is type safe in Ceylon, right? So if I write, you know, if I change this to, you know, just ignore this one, make. Then that's no longer well typed, right? Because it can see that this tuple type isn't assignable to the parameter list of this function. A lot of very cool things a lot of very cool functionality flows out of that, which in 3 minutes I don't have really time to talk about. But among other things, it provides the ability to write variant functions which abstract over function types, higher order functions which abstract over function types, things like compose, and abstract over functionality and stuff like that, which is a rather unique feature of Ceylon. So guys, thank you again for coming. I hope you got something out of that talk. And yeah, please try out Ceylon. Ceylon 1.2 is coming out very soon with a bunch of new useful stuff. And yeah, we have a BOF at what time? 7:30. Yes? I think it's at 7:30 tonight. And come and ask all your questions. You know, obviously, there's no way I can cover everything interesting about a whole programming language in this time. So please come along and ask whatever questions you guys have at the BOF. Thank you again.